So what I have written on the board here is known as the Grignard, reaction. And it's a reaction that's used quite often, and it's a way to extend a carbon chain, and make an alcohol. So our product in a Grignard reaction is an alcohol, and this is why I wanted to do it during alcohols and anywhere we had a carbonyl carbon, actually. And I kept forgetting to bring it up at the end, going off on my tangents. So this Grignard reaction won the Nobel Prize in 1912. And the big key is it has to be done in anhydrous conditions. So we can't have water present during a Grignard reaction. Okay? And it's kind of something interesting that happens. So you take an alkyl halide. It could be an alkyl bromide or an alkyl chloride, as we've seen. And usually you want it in the primary, on the first carbon, due to steric hindrance. But what Grignard figured out, is that, well, if I treat an alkyl halide with magnesium in the presence of an anhydrous solvent, diethyl ether is usually the one that's used. Now, I get this weird-looking complex. We have to go back and remember that my alkyl halide is polar. Bromine being more electronegative than carbon. Bromine's pulling the electrons, towards it, partial negative charge. This carbon attached to the bromine, partial positive charge. When I treat it with magnesium in a ether, this happens where magnesium somehow gets in between the carbon and the bromine, which is kind of crazy, but it happens. And by doing so, the magnesium now is partially positive and my carbon becomes partially negative because carbon is more electronegative than the magnesium. Now we call this product a Grignard reagent. And what we've really done is turned carbon, which is usually partially positive, likes to form that carbocation, we turned it into a nucleophile by giving it that partial negative charge with that magnesium. Now, we bring the Grignard reagent down, and we need to react it with a carbonyl carbon. Whether it's an aldehyde, a ketone, or an ester. Grignard reagents will not react with carboxylic acids. But it will react with aldehydes, it will react with ketones, and it will react with esters, and we'll look at a couple after this. So, the carbon's partially negatively charged. It's a nucleophile looking for positives, and it finds the positive in the carbonyl carbon, which I have in red here. Carbon's losing in the carbonyl carbon the tug of war to oxygen. Oxygen's got 2 lone pair on it and is more electronegative. The negative carbon attacks that positive, partial positive carbonyl carbon. When it does, the electrons, essentially, and if we want to make this complete, we'll put the 6 electrons around it, and we create this oxoanion up here that's negatively charged. Carbon is going to use these electrons that it's using to bond to magnesium to bond to this new carbon and increase our carbon chain by, in our case here, since we have ethanal, by 2 carbons. Here's the carbonyl carbon, and here's the carbon that's attached to it. The magnesium bromide cation kind of hangs out up here by the negative charge after it breaks away. Now we can't leave it like this. Okay? We can't leave it like this, so what we do is then treat it with an acid to reduce it and create an alcohol. Your product of a Grignard reaction or a Grignard reagent with a carbonyl carbon is always, always, always an alcohol. So this is a way of producing an alcohol from an alkyl halide, but it's actually increasing the number of carbon chains. So it's a pretty cool reaction to the fact that I can increase the number of carbons and create an alcohol. Now, I don't want it to be an alcohol. I just want pentane or something like that. Well, then you can reduce it even further. Okay, you can take your alcohol, and we've gone through alcohol reactions and how we can reduce them, and we can do that. Now, the reason we have to be water-free is right down here. Because if I make my Grignard reagent in a water environment, and even moisture from the air can cause this to happen, your Grignard reagent breaks down. Okay, so if I have my Grignard reagent down here, again, R means some carbon chain, we all know that, and I have water present. All right, the carbon's going to attack the hydrogen because the carbon is negatively charged, and the hydrogen in water is just acidic enough that the partial negative charge on carbon will rip it off. We make this product over here, magnesium bromide hydroxide, however you want to pronounce that. It's garbage. It doesn't do anything. And we basically take our Grignard reagent and turn it into an alkane. So I guess in theory, if you wanted to turn your alkyl halide back into the same carbon chain alkane, you could make a Grignard reagent, then treat it with a lot of water. But there's other ways to do that besides doing it that way. Okay. So it's a pretty cool reaction to the fact that I can increase my carbon chain right? Increase the carbon chain length and also turn it into an alcohol. So your product is always an alcohol. All right, questions on that? So let's look at a reaction with a ketone. Okay. Now I'm going to give us some Grignard reagent. Doesn't matter. Again, the magnesium is partially positive. My carbon that's attached. It's always going to attach to the carbon that is attached to the magnesium bromide. I'm going to add some ketone. Okay. Going this way. The carbon's partially positive. The oxygen's partially negative. My carbon of my Grignard reagent. Okay. leaves and attacks the carbonyl carbon, which in turn, let me do it in different colors here. Let's do it in blue. Which in turn causes these electrons to go upward. By the way, if I ask for a mechanism, this is what I'm talking about. Drawing arrows in. Okay, great at your last lab report. Some of you wrote me chemical reactions when I asked for mechanisms. All right, so we're going to get an intermediate here. Our intermediate is going to be a carbon of the carbonyl carbon. Okay, that's bonded to the ox anion. And the original carbon chain is attached. So that's this R right here. Let's do it in blue also, so we could follow that carbon. Now the magnesium bromide, again, we're not really worried about it, but it is sitting up here, hanging out, positively charged near that. We take it another step, treat it with an acid, and we end up with our alcohol, and we actually end up with a tertiary alcohol in the process. The key is making that Grignard reagent. Once we make that Grignard reagent, we are pretty set to go as long as we have a carbonyl carbon. We need a carbon that's partially positive, and a carbonyl carbon is partially positive enough that the partially negative carbon in the Grignard reagent will attack it and increase the carbon chain length. Okay. Now, what about an ester? Well, an ester is a very interesting compound to see in reaction with a Grignard reagent. Okay. Wait till you see this. It's pretty cool. You can actually increase the carbon chain by 2 Grignard carbons. Okay, so let me get red out here. So let's say we have our Grignard reagent. Okay. MgBr. And we're going to add to it an ester. Okay. I'm just going to do OCH3 just for space-wise. Okay, again, we have the same thing going on. Magnesium is partially positive. And due to our Grignard, my carbon's partially negative. Over here, again, same thing. Carbon is partially positive, and so this carbon is partially positive. Oxygen is partially negative. That means that this carbon's electrons that are used there are going to attack here. And we're going to get our intermediate. This is going to come up again. And our intermediate's going to look like the following. I've got my carbonyl carbon, which is now bound to the oxo anion, just like always. I've got my R prime, Okay, and I got my OCH3. Now, of course, again, I have my magnesium bromide hanging out up here. Positively charged. That's for you, Dylan, just so everything stays balanced for you, buddy. All right. And I've got my other carbon attached. Okay. From here. Now, our next step in our Grignard would be to treat it with acid and turn this into some alcohol group and have that OCH3. But with an ester, something interesting happens. With an ester, the intermediate that we have turns into a ketone. These electrons actually come back and kick this OCH3 off. It's pretty neat, and I'll show you why it's pretty neat. So I end up with something that looks like this. R prime bonded to a carbon, double bonded to the oxygen now. The OCH3 is kicked off, and I'm bonded to the original carbon from over here. I've created a ketone. The OCH3 is sitting off here as a minus charge, stabilizing, if you want to, stabilizing that magnesium bromide cation complex. And we create a ketone. So we've increased my carbon chain by whatever the carbon chain on the Grignard is. But what I also did was recreate a carbonyl carbon, which allows me to do this. Treat it with a second Grignard reagent or a second dose or a second molar amount, as long as I have excess of the Grignard reagent. Have this come back in and attack. Have these come back up. Have an intermediate that looks like this. Then treat it with, I'll go like that, with our acid, and end up with a product of an alcohol eventually that's bonded to two new carbon chains from our Grignard reagent. So with my ester, I get to treat it twice with Grignard reagent that I created earlier on. The Grignard reagent you create earlier on is all dependent on, what carbon chain you're looking for and so on. So this is a pretty cool reaction that ends up creating an alcohol, and you end up creating it from starting with an alkyl halide, treating it with magnesium in anhydrous conditions, so lack of water, ether, creating your Grignard reagent, and then combining it with a carbonyl carbon of an ester, a ketone, or an aldehyde. All right, questions on that?